What does it mean to say that it does?
That you can apply any linear,
Can be
you can apply a
expressed as
linear
a linear
transformation to
combination
get any element in P2.
You can apply a linear combination of those elements to get any element in P2. I agree. In other words, do there exist constants C1, C2, and C3 such that an arbitrary element can be expressed as this combination of the elements of my set? I think I've just simply restated the question. In other words, for any a sub naught plus a1x plus a sub 2x squared, can I express any such element P2 as a linear combination of the elements, the three elements in the set I just listed? That's the question. So I think it amounts to this. To see if C1, C2, and C3s exist, I better be able to solve for them. And to solve for them, I guess I'll build a system of equations. Equating coefficients. Equating coefficients. Wouldn't the equation of equating my constant terms look like this? C1 plus C2 plus 0 is equal to my a sub naught. Equating coefficients of x yields the relationship to C1 plus C3 is going to be equal to my a sub 1. And lastly, equating coefficients of x squared, that suggests that C2 plus C3 is equal to my a sub n. Excuse me, I said a sub n, I meant a sub 2. I just need to solve for C1, C2, and C3. But isn't that a piece of cake? Did somebody say wait?
No. No, I'm just remembering last Wednesday's class. Equals 1. Equals 1.
I won't do that today. And I think in reduced matrix, life's a piece of cake. You guys, doesn't that just give me 0, negative 1's 1, negative a sub naught plus a1? And then my 0, 1, 1 a sub 2. But I think that gives me 1, 0, 0 something. I shouldn't say that. A 0, 1 something and a 0, 0 something. Let's talk about the somethings. If I'm not jumping around too much, you guys. Can I just multiply both sides of the second row by negative 1? If I add first and second rows, doesn't that give me this? If I add second and third rows, doesn't that simply give me this? I'm almost done. If I now keep my first two rows, but multiply the third row by 1/2. And finally, you guys, keep my third row as is, not touching it. I'm really sorry I've lost my voice today. If I merely add the second and third rows, I'm cleaning things up quite nicely, I must confess. Does that give me a positive 1/2 a sub naught minus 1/2 a sub 1 plus 1/2 a sub 2? That's a 2, not a 0. And if I take the third row times negative 1, add it to the first, I think that gives me 1, 0, 0 as desired. As desired, now I'll pay the consequence. Is that going to be a 3? I just lost it, sorry. Is that a positive 1/2 a sub naught? Plus 1/2 a sub 1? Minus 1/2 a sub 2? What does this really tell me? What does that last matrix really say?
Those are your constants.
Yeah, those are my coefficients, my C1, C2, and C3. This says no matter what I grab out of P2, look at that darn standard one, a general quadratic expression, no matter what it is, I can find C1, C2, and C3 in terms of the coefficients. I think that's what it says. I'm getting more and more sophisticated with my examples.
I think remind me to leave class early today.
0, 3 halves, 1/3.
0.
3 halves, 1/3.
Well, that's one solution. I mean, the set that he's describing is the plane, right?
Yeah, very
So
nice.
how do you find a set for?
Well, that's my question for you. Sorry.
I'd say that E1, E2, E3 will still work.
That's true. Those three elements satisfy the equation. Well, but this equation relates to components, not really the vectors.
Would you have to
So, I forgot the formula, but I know there's a way to get from the Cartesian formula for a plane, get back to the vector equation. Once you go back to the vector equation, there will be a spanning set with it. Kind of.
Yeah, as long as you strip it from any coefficients.
Okay.
Yeah.
So if anybody remembers that, do that.
We're mathematicians. We don't have to remember anything. We'll just make it up out of thin air. I like what you guys are saying. You're saying, look, back in Math 32, that's the equation of a plane. How many parameters do you need to describe a plane?
2, 3.
You need two, just two.
Two.
Just need two parameters. And so I think the spanning set will only contain two. An efficient spanning set will only contain two elements. Let's give it a shot. Where x of 3 was given as, x3 was, oh shoot, I didn't say what it was. I'll make up a name out of thin air. And let x of 2 be S. And I think that means x of 1 is going to be negative 2s plus 3t. So I think this set sitting right above me is nothing more than a set of all ordered 3 tuples, all ordered triplets, whose entries are negative 2s plus t. As it's 3 t's. St, where s and t range over the reals. But this is the same as a set of negative 2s comma s comma 0 plus 3t comma 0 comma t, such that t ranges over the reals. Oh, did I leave s out of it? Sorry. But this is the same as, oh, look at this, a linear combination of these two elements. Or how about if I use my spanning set notation? This is nothing more than the span of the set containing two elements. Or I could say in English, what you see above that brace is the spanning set for that vector space. Which, by the way, is points in 3 space are simply points on a plane passing through the origin.
So, just really quick, I know it's silly, but how did you split them up over here?
I just made up a name, a free variable, a parameter for x of 3 and one for x of 2, but then I realized x1 relies or relates to x2 and x3 in a very special third fashion.
Okay.
There's nothing unique about me letting x3 be t. I could have let x1 be t. I just, in my head, when I created the example, I realized it would be fractions.
So you let x3 and x2 equal t?
Yeah, but I don't have to. You could let
Or
x1 be w.
x2 equals s and x3 equals t, and then you just
Solve
solve them
the
in
other.
for. Okay, okay,
You
cool.
just need a relationship of 2 variables.
Yes, that third equation was just a relationship. I agree.
Okay,
So
so
when you
just,
went from your second equation to your third one, or rather your second set to your third set, you just reorganized the variables?
Yeah, and I took my hands, I split that one entry up involving s and t's into two different elements of R3.
Okay.
So that they involved only one variable in each.
So did you know it's a plane because it's going to have one less dimension? Like your span is going to have one less dimension? Is that what's going on over there?
That's a good way to put it.
Okay.
I like that.
Span has 1 less dimension than your.
Well, in this example, in general, that won't be the case.
Yeah.
Okay.
You know, you guys, I didn't say this, but when it comes to subsets, I think it's about, when it comes to subspaces, You know, a lot of people don't actually like saying, oh, I gotta show non-empty, closure for addition, closure for scale multiplication. A lot of people say, I gotta show it has a 0 element. Then show closure for addition, then show closure for scale multiplication. I'm a mathematician, I'll do it more general than that. You don't have to show the 0 elements in there, because if you're non-empty and you have those two closures, for free you'll get the 0 element in the set. So I don't like the notion of saying, when it comes to verifying subspaces, and you might find this in the books or online, check to see the 0 elements in there. That's not really what's necessary. But if you do have a subspace, it will necessarily have a 0 element in it. That's why people get away with doing that. I'm sorry, you guys, I'm just more tired than I think. Anybody, since I'm losing my voice, you have to talk.
Well,
Can you not do any work and just give me the answer?
you have 2 IQ matrices, right? Sorry,
How many?
3.
How many? 2?
We could do 2. It would be, the first one would be the identity matrix,
Very nice.
and the second one would just be it'd be just 0, B, 1.
Very nice. So listen to my choice of words in English. That means the spanning set is a set containing these two elements. This isn't the spanning set, this is the entire space. Do you guys understand that these two things are not the same? And if I ask for the spanning set, I'd be looking for this. I just like this SPAN notation because the span of the set containing these two elements is actually the entire vector space up here. So be careful with my choice of words in my notation. I want to be clear. Sorry.
How did you determine that? How did you know that the spanning set was those two matrices
I
specifically?
skipped way too much work. Let me clean here. I think S is equal to this. Just because of how you and I add matrices. But that's the same as this. And my definition of a spanning set is simply a set that has the following quality, that if everything in your vector space could be expressed in a linear combination of it. And that's why I think that is my spanning set down there. Now, could I change this to this?
Yeah.
Yeah, I think I could. Can I change it to this?
No.
No, that wouldn't span all of it. This would.
Because you're establishing A is 2 and B is 4. Yes.
I agree. Who cares what it is? As long as it said generates the same space.
Will these ever have any of the odd operations of addition and multiplication?
Sure, it can. You're awesome too. Mike?
So what is the difference between span and the stem arrays versus?
Just so I think what you see inside my circle in red, what's inside my circle in red is the spanning set for that vector space. But what you see circled in blue is all of the vector space. Because when I put the SPA in front of the set, it refers to all linear combinations of these two elements. This is the whole vector space, this is just a set of two elements. I think what's inside blue is infinitely many items. What you see inside red has a finite number of items, just two elements. This is a big, big difference. Chris?
If you take a set and you span it, and you contain
do, and I don't think it would be even appropriate to use the words spanning set if it generated more than what your set had in it. I would not use the terminology. Now, this could be true. Your spanning set might contain more than it needs, but still all linear combinations, the elements in the spanning set, are just going to be your space. Let me give you an example of that. Come on, everybody.
We just did that.
Yeah, the answer is clearly yes. See, I think the answer is yes. I think everything in P2 could be expressed in linear combination of those four elements. I don't think it's a very efficient spanning set, but it certainly is the case. I think it's very efficient because there's duplication in that set. And when I say duplication, I mean this. One element can be expressed in linear combination of the others. And I think if one element can be expressed in linear combination of the others, then that one element, x squared plus 2x, can be expressed as c1 times the first, I said the first, plus c2 times the second, plus c3 times the third. Do you guys mind if I write it differently? Do you mind if I write that differently again? Can you guys notice what's sitting in front of me? It's a constant times the first element in that set, plus a constant times the second element in that set, plus a constant times the third element in that set, plus a constant times the fourth element in that set, and that combination is equal to 0. But not all the c sub i's are equal to 0. This is a whole new notion that I now want to come into. It's called linear dependence. So consider a vector space V. This set of vectors of V, V1 bar, V2 bar, all the way down to Vn bar, is said to be a linearly dependent set. Provided you can find a linear combination of the elements in that set that is equal to 0. Where? Not all of the c sub i's are equal to 0. That's going to be my definition of having a set that's linearly dependent. I will also say that this particular set of vectors in my vector space to be linearly independent. Provided that if I force any linear combination to be equal to 0 vector, then it necessarily implies that c sub I is equal to 0 for all values of I. These are going to be my rigorous working definitions of linear dependence.
In the top definition there, did you mean to multiply V sub n by C
I
sub n?
certainly did, thank you very much. I apologize.
What is the superscript on CI?
S. C sub I is just an S, plural.
Alright, C sub i's.
So with the definition of linear dependence, you're essentially saying that counteracting the direction of the other vectors.
Yes,
In which case you can
Yes.
express as a combination of.
the linear combination of the other two.
And so you're getting redundant.
And that's why I kind of went to that backward example going in the other direction, so you can see that.
Okay.
Now, I think if a set only contains two elements, to see if you got linear dependence is this easy. See if one entry is a multiple of the other. Is that silly? Because if I've got a set of two elements, this one here. Notice that I can find a linear combination of these two. To be equal to zero element of P1. Where clearly C1 and C2 are not equal to 0 because one could be -2, the other could be +1. Back whenever I have one vector V1 bar, no matter what it looks like, being a multiple of the other, then this set right here has to be literally dependent after all. Notice this up here just simply says 1 times V1 bar plus this constant times V2 bar is equal to 0 vector. So in a set of two elements, you can always see if you got linear dependence that fast. See if one entry is a multiple of the other. Once you get beyond two elements in a set, it might be a little more difficult to determine if you got dependence.
So you can also say that you know that a set that's linear dependent, that set can be expressed as a span of a smaller set.
Even if one of the elements could be expressed as a span of the other.
Well, I mean, that set you have there right there,
Yes.
V1 and V2, can be expressed as a span of V1.
But the span of V1 is a complex collection of vectors. And so I wouldn't say the set is equal to it because it's not an infinite collection of vectors.
Plus,
You said, if I could show this is equal to the span of just V1, you're saying I have linear dependence. But technically speaking, these can't be equal to each other because this has infinitely many entries in it. This is all linear combinations of V1 bar, whereas this only has two elements. Do you see what I'm saying? Did you mean this, Chris? Because that's what you meant. Then you're right. If these two are equal, that means that set right there is linearly equal.
okay.
I think that's what you meant.
But if you have something like that, then how do you know which one is kind of, the one with.
Oh, it's not going to make any difference. Change that to a V2 bar on the problem.
So are linearly independent sets always equal to 0? Because you're saying.
No, but if I'm going to determine if my set is linearly independent, I will force that linear combination to be the 0 vector and see if it forces C sub I to be equal to 0. Shoot, that's chapter 2 material. It's just solving the system. So let V1 bar be a vector of a vector space. Is this equal to the set linearly dependent or independent?
Can you explain your notation there really fast?
LD for linearly dependent.
Okay,
LI for
okay.
linearly independent.
Independent, because there's no other elements.
It'll be linearly independent if any C1 times V1 bar being equal to 0 vector necessarily implies that C1 has got to be equal to 0.
Well, yeah, it isn't.
Is that necessarily going to be true? You just separated out cases.
What?
I think if V1 bar is equal to 0 vector, then this singleton set V1 bar is going to be literally dependent because I can find non-zero constants. I can multiply it to get the 0 vector. And I think if it's the case that singleton set, the V1 bar itself as an element is not the 0 element of vector space, then I think this set is trivially linearly independent. For this reason, if it's not the 0 vector, multiplied by constant outside is not going to give you the 0 vector right back unless the constant is equal to 0. Right? Matches my definition. Do you mind Brad, can I borrow your text?
Yeah. So you already assigned,
I did.
um,
You have to remind me what it was.
it was everything, all the odds, and then 24.
Got it, yeah. So, how about the exam is doing this? Because I am not going to test you on what I covered Wednesday in class. The exam will cover chapters 2 and 3. In chapter 4 up to section 4.6.
Now, I looked at your previous exam, and you didn't really have like a lot of like actual just solving matrices on there.
I never do
Do you
math
normally
31.
do you normally just
Because you already did it back in math 12 or 29.
math 12? So do you normally just want us just to understand the formal definitions of
Theory,
those
yeah,
more
the-
so than
The definitions.
okay?
And if I ask you to solve a system, I'll probably do something interesting.
Okay.
Instead of
That's
something
normally
boring like
scary. And I'm sorry, what part of chapter 4 did you say we were going to cover again on the test?
It's up to 4.6.
Up to 4.6. Oh, I'm not done.
What did we cover today?
What did we cover?
Which
Spanning
chapters?
says 4 point, well, subspace is 4.3 and spanning says 4.4.
Okay.
You
And
never
so
gave us
material that we cover tomorrow will be on the test too?
Yes, which is
Okay.
linear dependence and independence, which I started. I just didn't give you
Okay.
decent examples. And 4.6, which is so related on bases and dimensions of vector spaces.
Okay.
Can I ask you a question about the direction of this class?
Yes.
What are we gonna do with spanning sets?
What a good question. I don't like the notion of spanning sets because how, like you and I talked about earlier today, how maybe I can throw an extra element in there. It's not a very efficient one. So to force efficiency with a spanning set, I'll make sure it's linearly independent. And so if I've got a spanning set that's linearly independent, I'll do a lot with it. I'll call it my basis for my vector space. And I think the number of elements in it is going to be what I refer to as a dimension of my vector space. Now that's really important because I will prove to you this semester, I'll prove to you that I can create what I refer to as a one-to-one onto mapping from any n-dimensional vector space to Rn. That is so special, I'll give it a name, I'll call it an isomorphism. Meaning basically that Rn is equivalent to whatever my vector space looks like as long as its dimension is n. Oh shoot, that means everything is equivalent to Rn if I'm referring to vector spaces. And I get there by talking about dimensions. And I can't talk about dimensions without a basis, and a basis is just a linearly independent spanning set.
So,
Ties together that beautifully.
so once we do that, then we put on our roll number hats, right, and start pretending like we're working the roll number system.
Yes.
Because it is absolute.
Not only that, but now it'll be easy for me to go back to solving differential equations, and if I want to solve an nth order differential equation that's homogeneous, I will have n linearly independent functions generate all the solutions. Really cool stuff. I think.
Something's like tiny.
White magic. It's happy magic. Thank you. Okay, I have no voice left. I guess we're done.
Did you have another class today?
Tonight. Tonight. You can laugh at me all you like. I'm sorry.
I suggest not going straight to the math lab or anywhere else. I suggest staying away from where people will ask you questions.
Oh, Brad, you asked about going over the quiz. I'm so sorry.
When you did the
I wasn't trying to
subspaces,
avoid it.
when you did the subspaces, you more or less like covered the material, so it's,
I still want to see it
Will you text me 2 in the morning?
tomorrow.
Tomorrow?
It's about it.
Or text me